Hello again. In this video I'm going to be reverse engineering the front end of the BM869s. Basically what I want to know is if there's an easy modification that I can make to this meter to improve its robustness. This meter was damaged with a 10,000 volt transient. They had also supplied me with this BM839, and this meter was damaged with a 12,000 volt transient. So these meters, the way that they ship, are actually quite robust. They're certainly in a better class than the majority of the meters that I look at. So let's go ahead and get started. We'll pull this one apart and have a look at it. And so we can kind of just eyeball this. You can see this is the input. It goes through, looks like 4 resistors. It looks like these two are in series, and then these two are in series. These both run up to a set of PTCs, and you can see these go to these two MOVs off to this common MOV. My guess is this goes back to the ground point. So let's just have a look with our other Bryman. The only question is, does this MOV go back to ground? And it does. Alright, so basically they have their input. That goes to one resistor, which is in series with another one, which is in series with a PTC. These are all 1K. And then this goes back to a MOV. And then this whole thing is replicated. So they end up having another set of resistors with another PTC and another MOV. And again, these are all 1K. And then this common point goes back through another MOV. And then that goes to our common point. You can see that the one MOV is actually physically quite a bit larger than the first two. Looking at the 10mm part, it's a 1000 volt device. And the smaller 7mm disc is a 820 volt device. And again, these are both 820s. So again, these are the two transistors that I damaged. Right here and here. And again, to be clear, when I tested this meter, we also damaged those same two transistors. So I'm assuming, let's just have a look where this taps in at. So again, we're already in the resistance mode of the meter. So there's our common point of the clamp. And this would be the opposite end. So that's either going to go to here. Alright, so it looks like it's the other side. So it's this one here probably. Yep. Not that it matters much because they're the same for both the legs, so essentially off of the one leg we have two transistors that are sitting back to back. This goes back to ground, and again these are 2N 2 2s. Just a real common transistor. It's one of the meters in any of the mode where it's requiring the current source, like for example reading resistance. This becomes the source and then this is the input. So I expect this probably goes off to some resistor and then off to a control IC. This probably goes off to a set of high voltage resistors and then again into the control IC. So if a transient were to come in while this is reading resistance and this is driving, again these MOVs aren't going to do a whole lot. We need to clamp it to a very low voltage, so that's where these two transistors come in. I think what I'd like to do is try to replicate this circuitry. Then what I'd like to do is see if we could find a better set of transistors that may do a better job protecting this input. So what I'm planning to do is make a test fixture, and we're going to change this a little bit. So what I'm planning is to use two 1Ks in series again, and I'll use 1K PTCs, but instead of using the 820 volt MOV that they use, I'm going to use a 1 kV MOV. So this will be 1K, and the lower one will also be 1K. And then in this bottom leg, I'm going to use a 1.5K to replace that 2K essentially. I'll still use the 1K PTC, and then I'm going to change the MOV's voltage from 820 to 620. Basically what I'm trying to do is force more current into this lower common MOV. And what I'm trying to do is put more stress on the devices that I'm testing out here. In the past, what I've been using is this little proto board that I whittled out. This board was only set up for a single leg. If we remove this bottom leg, this board would be fine for that, but to do it like this, I'll need a new board. So you can see I've chopped up a new one. This is what it looks like. I'm just going to use a couple of standoffs. These will be my banana connectors. For the 1K resistors, again, I'll just be using these ohmite parts. Talked about these before. I've used these on other tests. These are a high surge resistor. You can watch my previous videos if you want to learn about these. For the lower leg, again, I'll be using a 2-watt part for this. Right, this is looking at our assembled test board. You can see this MOV is just slightly smaller. Unfortunately, I ran out of large body PTCs, so I've got these smaller ones here. We'll see how these hold up. Again, you can see our 2-watt 1.5K, and then our two 1Ks in series. If these break down, I think what I'm going to do is just replace these with a third resistor. Again, you can see the slits that I've cut in the board for the PTCs as well as the MOVs. Again, typically with this transient, these aren't going to have any effect anyway. They just have too much thermal mass to respond to this fast of a transient. Alright, so you can see I have our high voltage generator out and our high voltage probe. This is currently set for 2000 volts per division. You can see we're about 4.5 divisions up. So this is roughly 9,000 volts that we're going to start with. And again, we don't have any transistors installed yet. I just want to see how this thing behaves by itself. Looks pretty good. You can see this has really done a good job attenuating it. You can see we're now at 5,000 volts per division, and we're a little over 3 divisions up. This is roughly 16,000 volts, and you can see we're also at 50 microseconds per division, so 1.5 divisions up. So halfway up is about here, and you can see we're a little shy of 50 microseconds. And we're going to be running this without the transistors installed. If this can run without breaking down, I think this will be a good starting point. Alright, here we go. Of course, the LaCroix had to do a recal. You can see it definitely knocked down the transient, but it certainly broke down. I'm not sure exactly where at. Of course, that time it survived. Well, I wonder if we just had a little piece in there. Well, the board looks fine. Let's just give it one more try. Right, this is an old Keithley electrometer. All we do is just have a look real quick at our little board, and let's just see what we measure for resistance across this thing. Looks like about 5.9 gig. I'm assuming most of that's because of the MOVs. Alright, so I have some 2N222s that we're going to be using. And out of these are basically base emitter collector. And again, we'll just be strapping two back to back. And I'll install them right across these two gaps here. Alright, so you can see I've tacked in our two transistors. I'm going to be applying a 220 volt full wave rectified signal into the front end of the board. And then we'll be using our Bryman meter here to read the output voltage. So it looks like about 8 volts. Let's have a look. This PTC should be getting quite hot. And indeed it is. So it's doing its job. So about 8 volts is what we're looking for. The transistors themselves are remaining quite cold. And let's go ahead and reverse the polarity. Shouldn't have any effect other than switching over to the other transistor. It looks like they're fairly well matched. If you're curious why the sign doesn't switch, again, this is in AC plus DC mode, so you're looking at the DC component squared along with the AC component squared, and then you take the sum of the two and take the square root of that. So that's the calculation that this meter is performing. Alright, let's see what we get for current now. Should go up quite a bit. Oh yeah. You can see I have our generator strapped for about 8,000 volts right now. This will be a good starting point. I have a small Teflon block that I'm going to use to spin this board up off the bench. Okay, so this will be test 1 with our 2N222s. Once again, the LaCroix has to recal. Alright, that was 5 transients. Let's just have a quick look and see if we've damaged those transistors. So this is the one in the ground leg. See, that one looks fine. Does not appear to be leaking. Let's check the top one. Oh, you can see that one's already damaged. Yep. See that? It's a dead short. Makes sense that we're only going to damage the one. I'm not running both polarities. Yeah, so even with 8,000 volts, that's enough to damage it. Yeah, I'm kind of surprised. Alright. Let's try a different set of transistors. Alright, these are a little different transistor. They're rated for a little bit higher current and a higher voltage than what the 2N2222 was. course, they also cost a fair amount more. Okay. Looks fine. And let's have a look at the leakage current with this. Wow, that's quite a bit lower. Alright, so just like before, what I'm going to do is apply our rectified AC signal. I've got our Bryman BM869s set to the AC plus DC mode, and I'm going to enable the output, and that'll give us an idea where these two transistors clamp at. So it looks like about 10.5 volts or so. You can see the AC component is about 4.67. I would imagine that the one PTC here is starting to get quite warm. Oh yeah. But it doesn't look too bad. Right, again, this will be a roughly 8,000 volt peak. Right there it is. Let's just see if it passes one transient. Again, it looks like our bottom one is fine. Let's check the top. Looks good. Alright. Let's give it a few more. Alright, that's 5 transients. Bottom one looks fine, and it looks like the top one is fine. Alright, I think what I'm going to do is just let this cycle for a little bit. That was about 30 transients. Let's see if our diodes are still okay. That's the one in the lower leg. There's the one in the upper. Still looks real good. Alright, let's try turning the voltage up a little bit. Alright, you can see we're still at 2,000 volts per division. And we're now 6 divisions up, or 12,000 volts. And again, we're at 50 microseconds per division. So the halfway point, you can see we're right at 50 microseconds full width half height. Alright, let's go. See, it's doing a real good job clamping it down. Let's give it one more. It'll be 6 transients total. And again, let's have a look at the lower transistor. It looks fine. And again, this will be the upper one. Looks fine as well. What we'll do is go ahead and turn this up a little bit further. Alright, you can see we're still at 2,000 volts per division. And we're still at 50 microseconds. And you can see we're now 7 divisions up, or roughly 14,000 volts peak. And again, this would be roughly our full width half height, so just shy of 50 microseconds. And again, this generator uses a 2 ohm source impedance. we go, 14,000 volts. It's doing a real good job again clamping that down. Alright, again that was 5 transients. And let's just check our diodes. And this will be the lower one. Looks fine. Let's check the upper one. Oh, real good. Getting no signs of it leaking. Alright, let's retest our leakage current. Looks like when we started out we were at 25 picoamps. Yeah, I don't think we've had any effect on it at all. I think what I'd like to do is drop a couple of these transistors inside of that BM869s that they sent us and retransient test it. We may actually improve its robustness with these. Again, these transistors cost a fair amount more than the 2N2222s. Those are a very old style transistor. They're just a general purpose part. So these two transistors here and here that we're interested in pulling. Which looks pretty good for 50,000 cycles, don't it? Tell you, the big thing with these meters is you have to make sure that you've got the circuit boards clean. Currently this thing's measuring a 1 gigaohm resistor, and you can see it's reading 1.02 nanosiemens. When I first put this thing together I was reading about 1.8 or so. So it was off by quite a bit. I had to go back in and reflush that area out, and now you can see it's back to normal. So go ahead and put the cover back on. Alright. Right, again you can see we're in conductance. No leads attached. Looks like it's going to zero out. So let's try it again. This will be a 1 gigaohm resistor. Can't ask for anything more than that. This will be a 100 megaohm. And this should read 10. Very nice. Let's try it in resistance mode. This should be 40 megaohms. Looks real good. This is a 10 megaohm, 0.1%. This is a 1 meg, 1%. This is a 100K, 0.1%. This is a 10K 1%. This is a 1K 0.1%. This is a 100 ohm 0.01%. Of course, we're getting down to where we could probably zero this out. So let's just hit the rel. And now let's try our 100 ohm again. This is a 50 ohm 0.01%. This is a 1 ohm 1%. This is 0.5 ohms at 1%. Alright, this will be 100 microamps, 10 microamps, 1 microamp, and 100 nanoamps. Let's just try it in the milliamp range. So this will be again 100 microamps. Get in diode test mode. This is an open. And here's a single diode and 2 diodes in series. Let's just try capacitance. So this is with an open. Go ahead and zero this out, and this will be 150 picofarads. Dead on. This will be a 1 nanofarad. Dead on. And this will be a 0.1 microfarads. Looks good. And this is our 1 microfarad capacitor. Looks good. And 10 microfarads. And 100 microfarads. Looks good. And for temperature, again, this will be roughly 500 degrees Celsius. Looks good. And again, we can adjust this down to room temp. And a little over 1,000 degrees. Let's just set the pot back to the center point. So again, this will be roughly 500 and 505.0. It's fairly close. See, in millivolts, this will be about 118. Looks good. And 60 hertz, that's correct. So this will be AC plus DC, and again, you can see 118.4 millivolts and 118.4 for AC. That's because there is no DC content. Again, this will be 5 volts. Dead on. This will be 2.5 volts. AC, you can see it there. And the DC content is 0. That's because we have a blocking capacitor on this one. This is with it directly coupled, so we'll read 2.5 volts for DC and 2.5 volts as well for the AC. This should be roughly 30 hertz at 2.5 volts, and this will be 15 and 120. Let's just go over to the high voltage. So this will be roughly 70 volts at 3.2 kilohertz, and again, it should be roughly 60, and that is correct. Let's just try it with the VF mode on. So again, 2.5. I can't drive this hard enough to get it to read frequency using this box. Alright, so this is my original Brahmin on the right, and this is the new one on the left. You can see I'm applying a 1 kilohertz sine wave right now at 1 volt. What I want to do is just increase the frequency, and let's just see if changing out these transistors affects the roll-off. It shouldn't have any effect. I don't even think those are switched in. There you go. Let's just see if we can pick up the frequency. So 491 kilohertz right now. 490.9. So yeah, it doesn't seem like it's hurt the high frequency response of the meter at all. I think the next thing we need to do is transient test it, and let's see if we made any improvement. I'm going to start our testing off by applying our rectified AC signal, because the transistors that I've used to replace the 2N222s have a little bit higher VBE rating. I think these are roughly 7 volts, where the 2222 is 6 volts. So we've gained almost 2 volts of clamping, I think, with this. Originally, with the 2N2222s, it was like 8 volts, and this is about 10 volts. So I just want to make sure when I actually switch that in, that having those extra couple of volts isn't going to cause us any other problems. So let's go ahead and get started. We'll turn on our output, and you can see it's 115 volts or so. And again, I'll rotate the knob through all the settings. That's a little better. Okay, so the reason that this is showing 120 hertz again is because this is a full wave rectified signal. Again, DC wise, you can see we're at 240 volts. Alright, let me go ahead and functional test it. Let's just try it with resistance real quick. It should read an open. So yeah, I think chances are good that the meter's just fine. Alright, so you can see I have our ESD gun out. And again, I'm going to be applying 5 transients, both positive and negative, with the meter set in each mode. Then we'll perform a functional test on it. Alright, that's it. Tell you what, before we finish that up, let me just try something real quick. Assuming we didn't damage the meter, but let's just put some high voltage into this meter and make sure we're okay. Again, this is not all that accurate. You can see we're reading 1 kilovolt right now, and the meter's reading 1006 volts. So we can go up a little bit higher. There's 1100 volts. So no problems. Alright, let me go ahead and functional test the meter. Alright, you can see we're currently at 2000 volts per division and 50 microseconds per division. You can see we're roughly 2.5 divisions up, or about 5000 volts. So we just start our testing here, and then we'll work our way up. Alright, again, this will be 5 transients, positive and negative. Alright, let me go ahead and functional test it. You can see we're still at 2 kV, and we're 3 divisions up now, so 6000 volts peak. Alright, again, we'll be applying 5 transients, positive and negative, with each mode of the meter. Okay, that's it. And again, 2000 volts per division. You can see we're now 4 divisions up, or 8 kV. And again, it's 50 microseconds per division. So you can see 2 divisions up, we're right at 50 microseconds full with half height. And again, we'll be applying 5 transients, both positive and negative. Alright, the camera batteries died. We'll continue on. Alright, that's it. Alright, still 2000 volts per division. And you can see we are now 5 divisions up, or 10,000 volts. And again, this is 50 microseconds per division. 2.5 divisions up, or roughly 50 microsecond full with half height. And again, this is where the meter had failed previously, at 10 kV. Let's see if it survives now with these new transistors. Okay, let's have a look at it. When the transistors have failed, let's just check those modes. So this will be 118. That seems fine. My guess is the whole meter is going to be okay. Should be again 118. There you go. Let's just check temperature real quick. Again, this should be roughly 500 degrees Celsius. Looks good. And capacitance normally does work. This will be a 0.1 microfarad. Looks fine. Let's just check resistance mode, and normally this would be reading some low resistance. We'll put a 10 meg in there, and you can see that's fine. Let's just try it in conductance mode. Now, and again, this is with leads open in my hands. Let's just hang it on our 1 gig resistor. So again, this should be 1 nanosiemens. And you can see the meter is pretty much dead on. So let me go through and finish functional testing it, but it doesn't look like we've damaged it. Alright, again, we're at 2000 volts per division. And you can see we're now 6 divisions up, or 12,000 volts peak. And again, halfway up, you can see we're roughly 50 microsecond full with half height. Alright, here we go. Before we do that, let's just make sure that this is still working. Yeah, it looks fine. Yep, okay. Alright, let's just really quickly have a look at the resistance mode again. Alright, looks like it stayed open. Let's just hook up a 10 meg to it. See if we can pick that up. And no problems at all. Let's go to the other end. This will be a 100 ohm resistor. Yeah, it looks fine. This will be a 1 gig ohm resistor. Yep. Alright, let me go ahead and finish functional testing it. Alright, so the meter passed that test just fine. Again, we're at 2000 volts per division. You can now see we're 7 divisions up, or 14,000 volts. And again, this is 50 microseconds per division. So roughly 3.5 divisions up. You can see it's just shy of 50 microseconds. Zoomed in, this is 20 microseconds per division. So again, 3.5 divisions up. You can see it's fairly close to 50. It's a fairly big transient. I don't normally test the meters up this high. Just for fun, let's see if it'll arc across this gap. I'm sure the AGC tones that down. Try to catch it with the other camera. So again, pretty good sized transient. Alright, if the meter survives this, I'll probably stop here again. This is higher than what I normally run meters at. Again, that's 5,000 volts per division. And it looks like it's still okay. Let's go ahead and continue. Alright, the camera batteries just died. I think I had 3 transients on it. What I'm going to do is just give it a full 5. There you go. So 14,000 volts peak with a 50 microsecond full width half height. Let's just change it over to resistance. This looks good so far. Should be reading 0. That's pretty close, so let's have a look. This will be with a 100 meg. Should be reading 10 nanosiemens. Looks good. This will be a 40 meg. Should be roughly 25 nanosiemens. Looks good. And this will be a 1 gigaohm. And this should be 1 nanosiemen. Looks fine. Let's try resistance mode. And this will be a 10 meg. Looks good. This will be 50 ohms. Looks good. It'll take the meter a little bit to recover from this. There's 1 k ohm. Let's just try it in capacitance mode. So this will be 1 nanofarad. And this is 0.1 microfarads. Looks good. Diode check mode. It's with a short. And here's a single diode. Looks good. This will be the thermocouple input, so it should be roughly 500 degrees C. That looks fine. And this will be roughly 118 millivolts. Looks good. And 60 hertz, that's correct. Should see the same thing in AC plus DC mode. That looks fine. This will be roughly 5 volts. Looks good. It should be about 60 volts. Looks good. And roughly 70 volts AC. That's fine. And we should have roughly 70 here. That's fine. Should be a little over 2. That looks good. Again, 60 hertz. And this is DC coupled. And again, this should be 2.5 volts DC. This will be roughly 30 hertz. There's 15 hertz. And 120. Alright, so it looks like the meter's just fine. So it looks like with just a change of 1 set of transistors, we can definitely improve this meter's robustness. This thing originally failed with a 10 kV, 50 microsecond full width half height. So we definitely improved it. That was 4,000 volts higher than what this meter failed at originally. Well, I think that's going to be it for this video. Hope you enjoyed it. Till the next meter, later.